Welcome everyone, my name's Andrew and I'm going to be using a couple bits of the university's software in order to try and demonstrate how I can very quickly come up with a worked example that I can talk students through. So the example I'm going to be going through today is a basic week 1 fluids and thermofluids problem. And before I start, I'll mention that I'm using Adobe Captivate to record what's happening on my screen at the moment. And I'm using a very simple program, freeware program called Smoothdraw version 3 to draw anything I need, and I've imported a few different images of formulas and things like that, which I'm using within several layers. So I'll just move the screen around a bit and you can see that what I've got up here is the rest of the program, but I'm just using this white space here to actually do the demonstration, almost as if it was a whiteboard. So I'll move on to the problem. So we're saying that compressed air is pressurized to a gauge pressure of 140 kilopascals. Given a temperature of 25 degrees Celsius and an atmospheric pressure of 101 kilopascals and a gas constant of 2.869 by 10 to the 2 joules per kilogram Kelvin, we're asked to find the density. So as I said, this is a week 1 fluids and thermofluids problem, ENCOR2100. And we use what's called the ideal gas law to solve this problem, which relates the density, as we can see here, to pressure divided by the gas constant by temperature. And it's a very simple application. The biggest problem that students have with these sorts of problems is using the correct units. For example, we have 25 degrees Celsius given here, and we need to substitute that into the temperature slot of the equation. And where a lot of students will go wrong is they'll just use 25 in here, but in fact you need to be using degrees Kelvin. In almost all fluids problems, unless specifically stated, unless the formula has already allowed for it, you'll be using degrees Kelvin instead of degrees Celsius or any other temperature units. So we can relate those two by this simple formula here, that degrees Kelvin is equal to degrees Celsius plus 273. So adding these two together, we get 298 degrees Kelvin. Now pressure it is also necessary to use the correct units with pressure. So what we need to find is absolute pressure. So what we'll be looking at at this point in time is we're assuming we've got some sort of enclosed vessel, we'll say, so some sort of gas tank, and there is a gauge in there reading the pressure, and that is reading 140 kilopascals. Up there. So that's our gauge pressure, which is given here in the question. But what this formula asks for is absolute pressure, which is the addition of gauge pressure and atmospheric pressure, as demonstrated by this equation here. to be substituting these two. Okay. So we can then simply say, let's just ignore that bit for a moment because that was supposed to come up later. But we can then simply say that the pressure we're dealing with is our gauge pressure, as red here, plus atmospheric pressure, which, even if that wasn't stated, you can assume the standard atmospheric pressure is always around that 101 kilopascals. But it was stated, so we'll add these up and we'll say that pressure is equal to 140 kilopascals plus 101 kilopascals, so given 241 here. And so finally, substituting everything into this equation in the correct format, we need to convert kilopascals to pascals here, so we do that by multiplying by 10 to the 3. And other than that, these two values can be substituted in from what we've already got here. And finally, that comes out to our density is equal to 2.82 kilograms per meter cubed.